All right, this is Unit 731, Part 2. Now, we're going to go straight to the exercise 731, Problem 8. Now, what makes this problem more complicated is that even though I have 4 terms, and it's asking you for us to find the roots, or the zeros, or the x-intercepts, they all mean the same thing. But what I'm going to try to do here is to figure out the roots. So normally I would say factor, and normally when I have 4 terms, I try to do factor by grouping. However, and don't write this down, this is not going to work out. If I factor by grouping, you're going to notice that this part is just not going to work out. So as you can tell, unless I have the same thing in parentheses here and here, then factor by grouping does not work. So I am left with a problem here that where factor by grouping does not work. So my only other option at this point, all right, is to use a theorem called the rational zeros theorem. And what the rational zeros theorem says is this. If you have your leading term, right, which in my case, my leading term is 1, right, or leading coefficient, I should say, is 1x to the 4th. So I'm going to call that 1 here for my leading coefficient. And then my last coefficient, which for me, that's 15. All right, what you're going to do here is, those are not necessarily what I'm looking for, but I'm looking for the 2 factors, or the factors of those numbers, all right? So for example, on my leading term, or my leading coefficient is 1, so the factors of 1 could be 1 and 1, or negative 1 times negative 1. So down here I have plus or minus 1. Now, on my last term I have 15, so think of the factors of 15, like 1 and 15, 1 and 15, and 3 and 5. All right, so, but also I could have negative 3 times negative 5 and negative 1 times negative 15. So therefore I have all these factors. Remember, every plus or minus you see on here represents 2 numbers. All right, now we're lucky because on this one, if I divide all of these by 1 or negative 1, I basically get just what you see on top. Negative plus or minus 1, plus or minus 15, plus or minus 3, plus or minus 5, right? So what the rational zeros theorem says is that one of these can't be a root to the problem, all right? So let's see. We're going to start off by just plugging in a 1 and hope that that works. Now, whether that works or not, I don't actually know that ahead of time, and that's what actually makes this pretty tedious, is because I'm going to have to check them, all right? So let's start off with 1. So I'm going to do synthetic division with that original function, which is, let's see, 1. Notice that I don't have an x cubed term here, right? So again, I don't have an x cubed term, so I'm going to write a 0 for that. And I have a negative 8 now, and another negative 8, and a 15. So the goal here is to get a remainder of 0, because remember, from the previous video, I said that if you get a remainder of 0, that would make 1. In this case, 1 would be a root of the polynomial. So let's see. With synthetic division, let's see, 1 times negative 7 is negative 7. This is going to be a negative 15. 1 times negative 15 is negative 15. So yeah, we get a remainder of 0. So don't forget, when we have a remainder of 0, that means that in this case, x is equal to 1 is a root. All right, so there it is. That's one root. Now we're going to write the result of what we got here. All right, so notice that because we started with an x to the 4th, my answer is going to be 1 degree less. So this is going to be 1x cubed plus x squared minus 7x minus 15. Now, again, they want to know all the roots for this one. Okay, so if I want to know all the roots, what I'm going to have to do at this point is hope the factor by grouping works, but surprise, it doesn't. So I'm going to have to do the whole P over Q thing again. All right, so where P is the last coefficient, or the factors of the last coefficients, and Q is going to be the factors of, and I should probably write the factors here just to make it not as confusing. All right, so all the factors of P, which is the last number, All right, factors of 15, let's see, we have plus or minus 1, plus or minus 15, plus or minus 3, plus or minus 5. Now remember, the reason I'm saying that is because 3 times negative 5 is negative 15, or negative 5 times, or negative 3 times negative 5, or positive 5 times negative 5, they're all equal to 15. Right. Factors of q, which would be plus or minus 1. So my factors, oddly enough, this doesn't happen all the time, are the same factors as what I had last time. So we're going to try this out and see if it works for this next one, all right? Now, normally I start with 1, and hopefully that works. That may not work, I don't know. So let's try 1, positive 1. And then normally if positive 1 does not work, so again, I'm writing the coefficients of this, okay? All right, so I'm going to bring the 1 down. 1 times 1 is 1. That's 2. That's 2. That's negative 5. This is negative 5. So I have a remainder of negative 20, which means that 1 is not a root. So this one does not work. Okay, so I would have to try to say negative 1. And now here's the problem, right? Or here's the part that you're going to find rather tedious, is that I don't know a way for me just to tell you, yeah, this one's going to work out. You're going to have to guess and check here. Let's see, that's 0, 0, that's negative. Okay, this one's not going to work either. So 1 or negative 1 did not work. All right. So again, why does it not work? Because I'm supposed to get a remainder of 0. So that one does not work. So let's try 3. Okay, so we're going to do that again. So we have 1, that's a 3, this is a 4. This is a 12, this is a 5, that's a 15. Okay, so this one right here, 3 did work, right? Which means that 3 is another root of this function. All right, so now what I have left, remember what I started with was this right here. All right, so I divided this by some x, so now what I have left over is x squared plus 4x plus 5. Now, once I get to this point, remember, so far I found 2 roots, right? Just to remind you, this is one answer, this is another answer, okay? Now, to get the rest of these answers, yes, I could do the rational zeros theorem and do P over Q again, or because this is a quadratic function, I could use the quadratic, if it's factorable, factor it. But unfortunately, there is no factors of 5 that add up to 4, so I am forced to use the quadratic formula. So we have b squared minus 4ac all over 2a. All right, so I'm going to have to use the quadratic formula for that. So let's see, I would end up with a negative 4 plus or minus. All right, let's see, 4 squared minus 4ac all over 2a, or in this case, 2 times 1. So we have negative 4 plus or minus the square root. If you do all of this over here, you end up with a negative 4 over here over 2. So the square root of negative 4 would be 2i right, which is the same thing as having this as negative 4 over 2 plus or minus 2i over 2, so that means I can reduce this, so we have negative 2 plus or minus I. So this right here is 2 answers, right? So I have two imaginary solutions, 2 complex answers, and 2 real solutions for a total of 4, right? So I did all of that work just to find the roots or the zeros of this function, right? So all the roots of this function, in conclusion, would be x is equal to 1, I believe, x is equal to 3, and then I have 2 solutions here that says x is equal to negative 2 plus or minus I. Now, this is something that I'm going to repeat again, but I believe towards the end of this section, it asks let me read it. The fundamental theorem of algebra, right? So the fundamental theorem of algebra is something that I already talked about before, but I'm going to mention it here. The fundamental theorem of algebra is something very simple that we kind of already talked about in the past, but that says that your number of roots has to be equal to the degree of the function. So since this was a degree 4 function, right, this problem number 8, that is degree 4, that I must have 4 roots. And in this case, I had 2 real and 2 imaginary or complex. But really, real and imaginary numbers are a subset of complex numbers, right? So technically I have 4 complex solutions here, but that's what you need to know. So notice that I have 2 real, 2 imaginaries. They got to add up to the degree. Okay, well, as far as AB, the answer is exactly the same. It says, what are the zeros of the function? Well, that's literally the same question, just written a different way. All right, so on number 9, right, just to remind you, right, how would I figure out what p to the negative 3 is? This is a different problem, right? So let me rewrite this. So number 9, you have this function right here. And they ask you what p of negative 3 is. Don't forget that you can do that with synthetic division. I'm actually not going to do that one because it's the same thing as number 5 and 6 and 7. Now, the hope is that that gives you a remainder of 0, because if you do this with synthetic division, right, like we did previously, if you do this with synthetic division and you get a remainder of 0, then that means that negative 3 is also a 0, which would answer number 10. All right, so real quick, let's skip all the way to number 12. It says, what does the fundamental theorem of algebra and its corollary said about the zeros of this function, right? So notice that they give you this function, and it's asking you, what does the fundamental theorem of algebra tell you about this function, essentially? Well, in case you don't know, and I've already mentioned it, but since the degree of the function is 7, then that means you must have 7 complex roots, some of which are imaginary and some real. But they're going to add up. They're going to add up to be 7. All right, now the only problem is it doesn't tell us how many real solutions and how many imaginary. I don't know that. All right, but it will at least tell us that if you add the imaginary solutions and the real solutions, it should be equal to 7, right? So let's move on to what this is called part 2, actually. And I just want to show you that some of this stuff is perhaps not as bad as you think. For example, 15 through 22. All right, if you read the instructions, it says use the rational zeros theorem to make a list of possible rational zeros. It doesn't actually ask you what the zeros are. It just asks you to write a list of possible rational zeros. All right, so one more time. I guess this is worth repeating. All right, so in 15 through 22, the rational zeros theorem says that if you take the last term, all right, or the last coefficient, which is 3, right, we're going to call that P. P was the leading, or excuse me, not the leading, but the last coefficient. And I wrote that again. It should be the factors of the last coefficient. And Q are going to be the factors of the leading coefficient. All right, so in this case, P would be 3. So what are the factors of 3? 1 and 3, right? That's it. So this ratio right here, P over Q, would give you the list of possible zeros, right? So we have 1 times 3 and -1 times -3 would be the factors. Now for the leading term for us, that's 2. So that'd be plus or minus 1, plus or minus 2. Now, I understand this, right? That since this one right here, if I divide this one by, and that 3 by 1, I still get the same thing. So the first two factors are the same. But if I divide those two numbers in the numerator, meaning the top, and I divide those by 2, I would also get plus or minus 1/2. Again, I'm dividing essentially plus or minus 1 over 2. And I'm also dividing these two, so you have plus or minus 3 over 2. So those are all the possible zeros. Now, they may all be zeros. None of them could be zeros, but these are the list of possible zeros that you have now. That's all of this question 15 to 22. It doesn't actually want you to know what the zeros are. It just wants the list of the possible ones. So that's as far as you go on 15 to 22, okay? Once you get past that, for example, 23 to 28, then you have to kind of use your use the skills that you have gathered over hopefully this entire year and then make some sense of this. For example, in 23, I have this function and they're asking you to find the real zeros of this function, right? So if you happen to have imaginaries, I don't care about those. Apparently you just want to know the real zeros. When I look at this, I realize that this is factorable because it's a trinomial. So I have factors of 15 that add up to 2. How about 5 and -3? So this is x squared. Right, so I'm going to set that equal to 0. Remember to find the zeros. So if I set each factor equal to 0, okay, take the square root of each side. This will give me plus or minus, which is 2 roots, by the way. I squared is 5. If I set this equal to 0, that's going to give me plus or minus square roots of 3. Okay? Notice that these are 4 roots right here. All right? Now, since it only wants to know in this problem the real solutions, I'm just going to circle this, right? But technically, all of those are roots that I come up with. So not all the time are you going to have to do that P over Q thing. It's only when you absolutely have to, when there's no other way to factor it. You would kind of do the same thing. Let me look at my notes here. What number is this? 22. So for example, 22, no, that's not going to apply. Number says 27, okay. So let's go to so for example, number 27, yeah, like 27, you don't have a choice. You would have to do that. You would have to do that with P over Q, which is called the rational zeros theorem. 28, I don't see a way to do that. Let's see, yeah. 26, however, if you look at 26, well, hold on. Yeah, 26, same thing. That's a real shame. That's a lot of hard work here, right? But we're not going to do all of it. I'm going to save some of the work for the homework for yourself. Actually, 26 is a factor by grouping. Let's talk about 26. There is something weird about 26. You could do, right? So let's look at 26. Now, when I originally do factor by grouping on 26, that is not going to work. Okay? So sometimes, and you feel free to do this, or at least try it. So if I do factor by grouping as it stands, it doesn't work. But sometimes if you shift, or if you switch, some of these numbers around like I do here, and you do factor by grouping now. So for example, this is a -17x. That would leave me with a x squared minus 2. Yep. And then this one has a common factor of 5, so that would be x squared minus 2. So notice that this one is a factor by grouping. Now the question could be for you, like, how do I know when I can switch those? The answer is try factor by grouping as it is. If that doesn't work, try it the other way, right? Unfortunately for you and for me, there's not a one way that I can just tell you, hey, do it like this every time, right? You're going to have to use your brain, and you're going to have to figure out what the skills that you have and figure out all the possibilities. So in this case, again, this is much easier. I still don't have to do P over Q, which is nice. Set each factor equal to 0. So this one's going to give me x is equal to 5 over 17. And this one right here would be x squared is equal to 2. So that's going to give me x is equal to plus or minus the square root of 2. Okay, and now in this case, as I'm looking for the real solutions that would work. Now, I'm not going to do 27, but I am going to show you 27 on my screen so you can see how complex this can get. So this is 27, right? So notice that I did P over Q. There's no other way to do that one. And then I think, yeah, I had to do it twice, which sinks, right? And then once I got down to this part right here, once I got to this part, right, I got that from here, then I was able to factor to get the last two answers. But before that, notice that I had to do that once. Here's once. I got that. Here's that answer. I had to do a P over Q again, which is the rational zeros theorem. And then once I finally got the right answer, or the correct factor that gives me a remainder of 0, don't forget that's what we're looking for. That gave me the last two. And that would sort of look something like this. Okay. So let's see, what were my answers? 1/2, negative 1/3. Yep. Oh man, that stinks. Those are like the same equations. So this is kind of funny. I think these factors are the same 4 times. Like this happens twice, that happens twice. You couldn't know that before then. All right, so you can see the roots are the x is equal to negative 1/3 and x is equal to 1/2 with a multiplicity of 2 because they happen twice. All right, so again, this could be very involved. And then finally, let's look at, we'll do one more here. And this one, I'll try to make it short. Okay, so let's look at 29 and we'll quit here. Okay, so after 29, we can quit. Because again, this do take quite a bit of time. So in 29, notice that they're asking you to find all the zeros. All right, and they actually want to know then completely find all the zeros, then completely factor over the real and complex numbers. Okay, so I basically want to find all the answers here, right? So all the zeros. So this is 29. So one more time. Try to do factor by grouping on this one first. Try it out. It doesn't work. And then P, which would be this right here, will be the factors of the last coefficient or the factors of the leading coefficient. All right, so notice that the leading coefficient is 1. So this is going to be plus or minus 1. And then up here, that's kind of nice because the only factors of that is plus or minus 1 and plus or minus 5. Which leads us to the only factors that it could be this. These are the list of possible zeros. And I'm going to do factor by, I'm going to have to do synthetic division to find out 1. Now, I kind of already did this ahead of time, so I can tell you that 1 and negative 1 does not work. So the next thing, I don't think, 5 doesn't work. So the only one that I was left over with was negative 5. All right, so notice I'm going to write a 1, a 6, 6 again, and a 5. And my hope is, if this is a root, I would have a remainder of 0. Don't forget that. So that's going to give me a negative 5. That's a 1. That's a negative 5 again. That's a 1. That's a negative 5. So that's a 0, okay? So that means that x is equal to negative 5 is a 0 of the function, which is great, all right? Now the next thing is I'm going to try to see if this right here, which is now 1 degree less than this, all right? So this is degree 3, so that's going to be degree 2. X squared plus x plus 1. Okay, so I have that. I have to figure out if that's factorable, and it's not factorable, so guess what I get to do? If you guessed quadratic formula, you would be correct. So I'm going to write the quadratic formula here one more time. You don't have to write it more than once, but if you don't have it memorized, well, you should probably write it more than once. So this would be -1 plus or minus the square root of 1 squared minus 4ac all over 2a, a being 1. So we have -1 plus or minus, let's see. This would be 1 minus 4. So it's going to be a -3 all over 2. So this right here would be a -1 plus or minus I square roots of 3 over 2. So this are my, because this original function was degree 3, these are my other two roots. So those are all the roots that are in there. All right, so we have 3 roots total. Now the question said find all the zeros of the polynomial, which we did, then factor it over the real and complex numbers. Oh, so you should graph this problem to check your answers. Well, we're not going to graph it, but if you were to graph it, it would only cross the x-axis at -5. Right, so again, sorry for how long this is, but this is probably the most complex part of your of this class, honestly, probably of the entire semester. So best of luck to you. Try to do the homework. I'll try to see if I can find a video or two that are not mine that talked about the rational zeros theorem, so maybe you can see that from another perspective.